All right, so today we're going to begin a brand new unit, and this unit is called complex numbers. Okay, so our first lesson is on something called imaginary numbers. You may have heard of these before. They're one of the more famous, I think, types of numbers in math. Are infamous depending on who you ask. So let's start with a problem from the previous units. It says solve this equation, x squared plus 1 equals 0 for a domain of real numbers. So I'm going to solve this equation. When I try and solve it, I cannot factor it because that's not a minus. If I had x squared minus 1, that'd be a difference of two squares, but we don't have a sum of two squares. So I'll use square roots. I'll isolate the x squared. Then I'll take the square root of both sides. But we have to use plus or minus. But then what happens? Yeah. So this is no real solutions. Because I can't square root a negative number. However, what if we could? What if I said we can square root a negative number? Now, I always say it's not a real number because there's no real number that if you square it gives you a negative number. It doesn't happen, right? Negative 1 squared is positive 1. But what if there was some number that we just didn't have yet? And I'm going to call that number I, which is called the imaginary unit. Numbers which include an imaginary unit are called imaginary numbers. The set of numbers made up of imaginary numbers and real numbers is called the set of complex numbers. So we have two distinct disjoint sets, no overlap. So it turns out that every complex number is either real or imaginary, not both. Taken together, that full set is called the complex numbers. I is equal to the square root of negative 1. Therefore, I squared, if I square both sides, squaring the square root of negative 1 is negative 1. Now, let's work example 1.2, solve it for the domain of complex numbers, and then we'll check our solutions. So I'm going to subtract 1 from each side. I'll take the plus or minus square root of each side. And we know that the square root of negative 1 we call I. You could essentially think of I as just simply an abbreviation for the square root of negative 1. So apparently the answer is plus or minus I. But don't take my word for it. Let's check our answer. So let's start with I. I squared plus 1. Does that equal 0? Well, as we talked earlier, if I is the square root of negative 1, then I squared must be negative 1. And that's a true statement. What about negative I squared? Well, we plug it in parentheses. Negative squared is a positive. So that negative is going to go away when I square it, and I squared is negative 1. So that's also a solution. So we have two complex solutions, I and negative I. I recommend you put a little tail in your eyes. Okay. Now, just a quick statement about this. The requirements that a solution be a solution is that if I plug it in, it makes a true statement, like we've shown here and here. There are no requirements for solutions to be pretty or for you to like them, right? So it seems weird, and you may not like it, but they're solutions. Hey, using complex numbers is great and all, but they would not be very useful mathematically unless we were able to perform all of our favorite operations like add, subtract, multiply, divide, etc. with them. Unfortunately, we can. So the complex number system is what we call a consistent system. I don't know when I go through all of the history of this. I'm probably going to be saying this, more than once, it looks like. Maybe. Yeah, I go over it here. But I guess we'll wait on that. We'll wait on that. I can talk a lot about that. But for now, let's just leave it as imaginary numbers form a consistent system where we don't get one result one time, a different result another. That would be inconsistent, and math wouldn't work very well. All right. So we'll talk about some properties of complex numbers. Complex numbers can be expressed as a plus bi, where a is the real component and b is the imaginary component. If b does not equal 0, then there's an I, therefore it's an imaginary number. Complex numbers are closed under addition and multiplication. That is, the sum and product of two complex numbers is always a complex number. While a real number exists on the real number line. We've been dealing with number lines. We deal with them with inequalities. You learned about them in middle school. You may have even had a math teacher that decorated their entire room with a real number line. Negative numbers to the left, positive numbers to the right. Imaginary numbers cannot fit on a number line. Instead, they have to fit on a complex number plane. So we're going to graph imaginary numbers the same way we would graph the points x, comma, y. And in fact, we can start thinking of x as a real number and y as a complex number, and we have exactly all the stuff that we know and love. So let's do 5, negative 4i. We're going to plot the number. All of your real numbers exist on that simple, boring little number line. Complex numbers require us to be a little bit more creative. So we're going to move to the right 1, 2, 3, 4, 5 on the real axis, which is like the x-axis, and down 4. So this is the point 5 minus 4i. Let's plot the point negative 6, 5i. Somewhere over here. I didn't give us a very good grid. I accidentally put a comma instead of a plus sign, and in fact, you'll see that from time to time. People talk about a complex number as being negative 6, comma 5, and they mean negative 6 for the real, 5 for the imaginary. All right, 7i. 7i has no real component, so it's just on the imaginary. That's 7i right there. We sometimes call that a pure imaginary number, and then a complex number that doesn't have a real component, only an imaginary. And then negative 5. This is a real number, and you can tell because it lies on the real number line. They're all complex numbers, right? We've had an infinite number of real numbers on this real number line, but now our numbers have expanded to a whole new dimension. Would you please practice graphing the complex numbers A, B, C, and D from practice 1.1? Okay, so basically it's the same thing here. We're just going to plot these points as if they're x and y coordinates, basically. So negative 5, 7i. I think it's somewhere around there. Doesn't have to be perfect. 10 is a pure real number, right? Just a real number. Negative 3i, that's a pure imaginary. Sorry, we don't say pure real. We just say real, but that's pure imaginary. And then 8 minus 4i, that is an imaginary number as well. So some imaginaries, some reals, all complex numbers because they all lie on the complex number plane. Okay, so the distance a complex number is from 0 is the same. We use the same words as we do for a real number's distance from 0. Does anyone remember what you call a real number's distance from 0? We call that the numbers what? Very good. Another word for that is the magnitude. Oftentimes we talk about magnitude of a vector, for those of you that are in physics or something like that. So absolute value is the size of the number, but not the direction. Exact same thing with complex numbers. We're simply looking for its distance from 0 without caring about its direction. So let's start with 3 minus 4i. So 3 minus 4i. Let's plot that. 1, 2, 3, 4. There it is right there. 3 minus 4i. So its distance from 0 is this distance here. Now, the absolute value is not 7, okay? Because that's not, I mean, I did go over 3 and down 4, but that's not the shortest distance back to 0. Does anyone think they know what the absolute value of 3 minus 4i is? Which is written like this. Well, what was this length here? Let's see. This was how far? 3, and this was 4. And that makes a right triangle, so 3 squared plus 4 squared, square rooted by the Pythagorean theorem, which is the square root of 9 plus 16. That's 25, and the square root of 25 is 5. Or what you might call a 3, 4, 5 right triangle. So the absolute value of 3 minus 4i is 5. Just like before, the absolute value will always result in a positive real number, or 0. All right, let's talk about the absolute value of 4i. Now, 4i, that one's a little easier. 1, 2, 3, 4, that's right here. So because it doesn't have a real component, it's easy to see that the absolute value, I shouldn't say equal, they're two different things. The absolute value of 4i is 4. All right, let's try the absolute value of negative 5 plus 5i. Let's see if we can figure out what that would be. So that's 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5 here. That's negative 5 plus 5i. So again, I got a right triangle here. Negative 5. Well, that distance is just 5, right? Because we're doing absolute value. So I need to take the square root of this squared plus this squared. 5 squared is 25, so that's the square root of 50. Which is 5 times the square root of 2. So the absolute value of negative 5 plus 5i is 5 root 2. All right, for practice 1.2, once again, I'd like you to plot and then use the Pythagorean theorem to find the absolute value of each number. Make sure you notate that it's the absolute value like I did. I don't want you thinking that negative 5 plus 5i equals 5 root 2. That's not true. The absolute value of it equals 5 root 2. And I'll give you a minute to do that. All right, let's see how we did. So, negative 7. That's just a real number. So the absolute value of it is just 7. 6 plus 8i. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8. That's like right somewhere over there. You might recognize that as we saw earlier, the 3, 4, 5 Pythagorean triple, 3, 4, 5. This is just a 3, 4, 5 multiplied by 2. So this should be a 10. 6, 8, 10. But that's 6 and that's 8. The absolute value of 6 plus 8i is the square root of 6 squared plus 8 squared. That's 36 plus 64, which is 100. So it's 10. Last, we have the absolute value of 2 minus 5i, which is down here. So that's a right triangle with a base of 2 and a height of 5. So it's the square root of 2 squared plus 5 squared. So that's 4 plus 25, which is the square root of 29. Now 29 is prime. There's no pairs or anything like that for me to simplify, so I just stop there. Okay. Okay, as we discussed earlier, they are a consistent number system. So we can add, we can subtract, we can multiply, and we can divide with them. So let's see how we can do this. Now, to be consistent, I want it to be what's called closed. Closure means that when you take two numbers and perform the operation, the result is a number of the same type. So, for example, the even numbers are closed under addition. If I take two even numbers and add them together, I end up with an even number, always. If I take two real numbers and add them together, I get a real number answer. You haven't ever added, 3 plus 7 and gotten something with an I in it, right? Same with complex numbers. If you add a complex number and you add a complex number, you'll get a complex number. Let's see. We know that all complex numbers can be expressed in terms of a plus bi. Now, a or b, one of those might be 0 or even both. Let's take a look. So, in fact, this works out just like combining like terms. Once I remove these parentheses, which are there just to emphasize that these are two different complex numbers, I can add the real components, 7 and 3, and get 10, and the imaginary component, 6i and minus I, and get 5i. Okay. Let's try the next one. Here, I'm going to distribute this negative to make it a little bit easier for me, and then I'll combine like terms. This time I just get negative 3. We said that the adding of two complex numbers should always result in a complex number because it's closed. Well, this is a complex number. Remember, the complex numbers include all the imaginary and all the real. It just so happened we added two imaginary and got a real. So you can't add two real and get imaginary, but you can add two imaginary and get a real. All right, now we're going to multiply, and you might be thinking this looks like multiplying binomials. It is. We're going to FOIL. So first would be 3 times 2 is 6. Outer is 3 times 2i, so that's plus 6i. Inner is negative I times 2, so minus 2i. And last is a negative I times a positive 2i, which is a minus 2i squared. But back on the first page of these notes, we talked about what I is. I is the square root of negative 1. If that is true, then I squared must equal negative 1. Because if I square that, I get rid of the square root sign. So we know what this is. This is a negative 1. So it turns out I squared just changes the sign. So I'll combine these things. This is 6 plus 4i. Negative 2 times a negative 1 is a plus 2. So my final answer is 8 plus 4i. All right, let's multiply just I times 3 plus 2i. I'll just distribute. I times 3 is 3i. I times 2i is 2i squared. But remember that I squared is a negative 1. So this becomes negative 2 plus 3i. All right, I'll let you work practice 1.3. All right, let's go over those. The first one, we should just combine like terms since we're adding, and this will give us 5 plus 5i. On the next one, we'll need to distribute the negative to make this easier. Makes this a negative 5 minus 4i. So this is a 4 minus 5i. And on the last one, we need to FOIL this. So first would be 9. Outer would be a minus 6i. Inner would be a plus 6i. And last would be a minus 4i squared. That actually cancels out. And I squared is a negative 1. So this is actually just 9 plus 4, which is 13. So these two things you might remember as being called conjugates. And just like before, when we had irrational numbers, we see that when you multiply a number and its complex conjugate, you get a real number. And we're going to use that to our advantage. So part C of the last practice problem demonstrates an important relationship. The product of a complex number and its complex conjugate, we'll just say conjugate, is always a real number. The conjugate of a complex number a plus bi is found by switching the sign in the middle. So the conjugate would be a minus bi. So if you have a minus, it becomes a plus. If you have a plus, it becomes a minus. Now, there are several applications of complex conjugates, but we're going to use the complex conjugate right now to help us divide. So the reason why we need to do this way is because I cannot easily divide a binomial by a binomial. I need to use a conjugate to make this work better. So to divide two complex numbers, you may have noticed we didn't do division yet. That's because it's a little bit more complicated. What we do is we multiply the numerator and denominator by the conjugate. Because that's going to result in a denominator that's a single real number, and it's easy to divide a binomial by a single real number. So now, when I multiply the numerator, I'll need the FOIL. 3 times 2 is 6. 3 times a negative I is a minus 3i. Negative I times 2 is a minus 2i. Negative I times negative I becomes a plus I squared. Now on the bottom, I'm going to go ahead and show this. I'm going to go ahead and do all of the foiling out, but very quickly I hope you'll see a pattern and it'll cut down on how much work this takes. So we'll FOIL again. 2 times 2 is 4. Outer would be 2 times a negative I, so a minus 2i. Inner, I times 2, so plus 2i. And last is I times a negative I, which is a negative I squared. But just like before, those will cancel out. The I squared is a negative 1. So this up here is just a minus 1, but this down here is actually a plus 1 because it's a minus negative 1. So on top, we're going to end up with 6 minus 1 is 5 minus 5i over 4 plus 1 is 5. Now that I have it like this, I can easily put my answer in a plus bi form because I can always divide a binomial by a monomial. That means 2 terms by 1 term by simply dividing this into each number, distributing it. So when I distribute, I get 5 divided by 5 is 1, and then 5i divided by 5 is minus I. So 3 minus I divided by 2 plus I is 1 minus I. We could check that by simply multiplying those two together and seeing if it gives me 3 minus I. It does. All right, let's try another one. Okay, I'm dividing a real number by an imaginary number. It'd be easy if this was the other way around, but I've got this binomial on bottom, so I'm going to have to multiply by the conjugate. I will distribute on the top. There's parentheses here. 5 times 3 is 15, and 5 times 2 is 10, so 10i. On the bottom, 3 times 3 is 9 for the first. The outer is plus 6i. The inner is minus 6i. And the last is minus 4i squared. So this becomes 15 plus 10i over, well, those cancel out like we expected. I squared is a negative 1, so that's just going to become a plus 4. Just going to change that sign. And 9 plus 4 is 13. Now, we could leave our answer like this, but just to show that it can be put in a plus bi form, I'll call it 5/13 plus 10/13 I. Either one is fine. Okay? If you just prefer to leave it like that, I'm okay with that. So, again, I've got a few more practice problems for you to do, so go ahead and try that, please. Okay, let's see how we did. All right, for A, you should multiply the top and bottom by 3 plus I. When you FOIL this, 1 times 3 is 3. 1 times I is I. I times 3 is 3i. And then I times I is I squared. On the bottom, 3 times 3 is 9. 3 plus 3i is 3i minus 3i. And then a negative I squared. And we knew this middle terms, the outside and inside, would cancel. All right, I squared we know is a negative 1. So that's a minus 1. This is actually a plus 1. So 3 minus 1 is 2. I plus 3i is 4i. And 9 plus 1 is 10. We can reduce this further. You could call this 1 plus 2i over 5 because I can divide each thing by 2. Or 1/5 plus 2/5 I, or 2i over 5, however you wish to say that. On B, this one has got a little bit of a subtlety to it. There's several different ways you could do it. You may have multiplied by negative 3i over 3i, negative 3i. That is the conjugate, and that does work. But when you don't have a middle term, a real number term here, you can actually just multiply by 3i and 3i. So it gives you 15i plus 6i squared. And that's a 9i squared. And like I said, you can certainly multiply by a negative 3i and a negative 3i. You just end up having an extra negative to factor out at the end. 15i, and then that's going to become a minus 1, so a negative 6. So I'll put the real number first. And then I squared is negative 1, so that's a negative 9. Once again, I can reduce each thing by 3. There we go. And like I said, you end up with a very similar answer if you multiply by negative 3i. I think you end up with 2 minus 5i over positive 3, which is the same thing. So we can use the pattern for squaring a binomial to help us square imaginary numbers. We know we're going to need to square these things, so they are binomials. Remember that a plus b squared is a squared plus 2ab plus b squared. So practice squaring 2 plus I squared using the pattern. You don't need to write out 2 plus I times 2 plus I and FOIL it. Use the pattern. Take a second and do that right quick. Okay, so when we square a binomial, we square the first thing. 2 squared is 4. Then you multiply the two things together, so 2i, and double it. So it's plus 4i. Then we square the last, so plus I squared. But I squared is a negative 1. So this is just 3 plus 4i. Okay, so the pattern when you square a binomial is a squared plus 2ab plus b squared. So I'm going to square that. 2 squared is 4. Then 2ab, so multiply these two things together and double it, making it 4i. Then square that, making it I squared. But I squared we know is negative 1. 4 minus 1 is 3. All right, let's try the next one. Square, this is A and this is B. So square A, 16. Multiply A and B together and double it. Again, we're following this pattern here. So 8 times 2 is 16i. Then square that. That becomes 4i squared. Got to square the 2 and the I. But we know that I squared is a negative 1, so this x becomes a minus 4. 16 minus 4 is 12, so this is 12 plus 16i. So with that, we can actually confirm solutions to more complex quadratic equations. Quite literally complex. So x squared minus 2x plus 5 equals 0. I want us to confirm that this is a root. Let's do this one together. I'll replace x with 1 plus 2i. Now to square 1 plus 2i, let's use our binomial squared pattern. Square the first, the a, that's 1 squared is 1. Multiply a and b together and double it, so 1 times 2 times 2. Square the last. I'll distribute here, negative 2 minus 4i, and then plus 5 is equal to 0. We know that I squared, though, is a negative 1, so this is just 1 plus 4i minus 4, because negative 1 times 4, minus 2 minus 4i plus 5 equals 0. Now, if this is true, everything should cancel out. You see the i's are gone. Now I got 1 minus 4 is a negative 3. Negative 3 minus 2 is a negative 5. And a negative 5 plus 5 is 0. So it works. So I just want to talk, and you can read this. I don't know if I'll read it to you, but I want to talk just a little bit about imaginary numbers. The great Rene Descartes, kind of almost the author of so much of this course, he is known to have criticized his associates, his contemporary fellow mathematicians that got into this. So this all started around that time, a little before calculus, early 1600s maybe. And Rene Descartes, the great algebraist, criticized what was going on. And he said, y'all are just studying imaginary numbers. And it always makes me think of the story of how Americans got called Yankees because they were made fun of as being Yankees, and then we took it as a badge of honor. Well, that's exactly what happened, according to some historians, that those studying imaginary numbers thought that actually sounded cool. But I don't want you to let the name confuse you. Imaginary numbers are no less real than real numbers. In fact, I'd argue that neither of them are real. Numbers in and of themselves are abstract concepts. You can't walk down the street and see a 5. You might see 5 of something, but you don't actually see a 5. Throughout the history of mathematics, new numbers have been discovered. Soon after imaginary numbers, something extraordinarily important was discovered by Sir Isaac Newton and his rival Gottfried Leibniz, found called infinitesimals, which are an important building block of mathematics. But throughout history of mathematics, there's been the discovery of new numbers and a bit of a reaction to it. We know Pythagoras loved right triangles, right? But he didn't believe in irrational numbers. Pythagoras believed that all numbers can be expressed as a ratio. And as the story goes, Pythagoras was, the story usually entails a boat, was on a boat with a student of his who explained to him that that is not true, that there must be some right triangles where the hypotenuse is not a rational number. And Pythagoras did not believe him. We know about pi. We know about square root of 2. We know about decimals that never repeat, right? We're comfortable with that idea. He was not. And as the story goes, what do you think he did to the person that the student that told him that irrational numbers exist? Well, believe it or not, the story is that he murdered him. That's how passionate Pythagoras was. The Greeks didn't have the number 0. Can you imagine doing math without the number 0? They probably would have thought the concept of 0 was ridiculous. How about negative numbers? There was a lot of time in history where humans did not understand the concept of negative numbers. And we could see that as children develop, negative numbers is something introduced later because they really struggle with it, right? But imagine trying to do some of the things that we do without them. Well, the same is true with imaginary numbers. Imaginary numbers were actually not developed as a way to get the answer to x squared plus 1. Nobody cared about that. They were created to get the answer to harder problems. And it turns out there are harder problems that you can use imaginary numbers as an intermediate step, and then later on you don't have any imaginary answers. And that's where the conflict came. They came to Rene Descartes and they said, look, I got this answer. And he said, but you only got it because you took the square root of a negative number earlier. And they're like, yeah, but later I squared it and it went away. And he said, but, the answer worked. So you see, imaginary numbers can get real number values. In the real world, in pure mathematics, imaginary numbers are extremely important and interesting. Pure mathematics doesn't really care about the real world, though. But in the real world, imaginary numbers are absolutely used. Air traffic controllers, electrical engineers, software developers, and statisticians are all known to use complex numbers. And of course, we certainly wouldn't have quantum mechanics, and we wouldn't have the advanced relativistic physics. So the two most exciting branches of science right now, Einstein's relativity, Heisenberg's uncertainty principle, Schrodinger's equation, and we all know about Schrodinger and his cat. All those things use complex numbers. Why? Because imaginary numbers can make real-world problems easier to solve. That's why we always use numbers. It makes our life easier. So with that in mind, I would like to show you some of the stuff from pure mathematics and maybe give you just a second to enjoy something about imaginary numbers. So what I've done is I have coded a complex number plane plot. So this is called the Julia set. So this here is a complex number quadratic equation. So instead of x squared, I'm using z. Z for imaginary numbers. So this is f of z, and my imaginary number is of the form a plus bi, and the origin is right here, okay? As I go to the right, those are real. Up is positive imaginary, right? So a number over here would turn out to be about 1 plus 1i, because this is actually just negative 1.5 to 1.5. And what I've done is I plotted them using this equation of z squared plus an imaginary number that's set by these two components. And the colors indicate how quickly the number, as I put it back in this equation over and over again, go to infinity. And what's neat about this is you can zoom in, and you get these self-repeating patterns called fractals. And so as I zoom in on this, you might see the image start to reappear again. And you see a little branch you want to go after and explore, you can click on it. But as you click on it, I think you'll see that more of the same starts to appear again. Now, this is only a difference of 0.001 from left to right. So we're already zoomed in very close. And you'll see my window settings eventually will min out, and it won't even show you how the difference is so small. This is this equation. But yet again, we're getting that little, it looks like somebody's hand almost, right? So these fractals are very important in making, along with some other types of equations, this really advanced computer graphics, because this became a way for us to simulate real natural coastlines, trees, leaves, mountains, all sorts of stuff. Use this. And I'll just reset my Zoom. Well, anyway, I played around with this, and you just have to install Java, but you can download this from my webpage if you want to play around with it. But I put in a couple of ones that I thought were interesting. Some of them are better than others, and I liked this one. It has kind of a bright, so the color comes from how quickly the numbers go to infinity as you put them in there over and over again. But I like these little black spots, because at first you're like, what is going on there? But if you keep zooming in on one of these black spots, you finally get some of that detail that we saw before. And it slowly starts to take shape. And you're seeing that fractal kind of nature slowly come out. So those little tiny dots that we saw before are actually much more intricate than you may have imagined. So the black means that put into this equation over and over again, the values go to zero. The yellow means that slowly, but eventually they go to infinity. So even though at first it looked like just a simple black dot, as we zoom in, we see we have these cool coastline designs. We have kind of that spirally finger kind of thing coming out. And just a couple more I want to share with you that I found. Here's one again. I'm using 0.59 for the imaginary. I'm just changing the real component of this number here. Oh yes, I remember. I loved how they had these big black circles in the middle, and they make almost a sunflower design, where the seeds go around. That pattern. Oops, I went too far. I'm gonna go reset the zoom here. You have to wait a little second, because it actually has to run through and recalculate all of these values each time. Oh, and the gold is an interesting thing. These are like channels where it's going to infinity much faster. I'm not sure why that happens, but I kind of like this empty space here. Now, what's interesting about this little black dot here is that it definitely has a finite area. You can see it is definitely fully enclosed. But this is a geometric shape with an infinite perimeter. Because as I zoom in on the coastline of one of these little black dots, you'll see that coastline is infinitely intricate. So I can zoom in forever and just get more and more detail to emerge. Now, unfortunately, my programming is not the best. You'll see we're already losing some resolution here, but you get the idea. With better programs and run, usually they run simulations, and they can take a while to render, and then show it as a video. You can get much more intricate ones. All right, well, I got one more I want to show you. I'll type in 0.3 and 0.3. So we'll look at some positive real numbers. And these are called Julia sets, by the way. Okay, look at this little cool shape here. It looks just like a little blob, right? But what I wanted to share with this one is, don't be fooled by a simple Julia set. So we have black, which is going to zero, blue, which is going to infinity super fast. So there's this kind of sharp border between the two. But as we click in, once again, we start seeing that there's detail there. And each spot that you click in has a kind of a different little nuance to it, a little coastline. This one seems to have a pattern for a little while, but we can zoom in more, and this little bay here, right? Almost. And this is all made with complex numbers. Because remember, this is the complex number plane put into a complex equation. That detail will continue to reemerge again and again. Just when you think you found the flat edge, you see it's more detailed than that. And that's it. So again, feel free to download that app. You have to install Java if you don't have it already on your computer. But I hope you feel somewhat motivated to study imaginary numbers because they're, well, they're beautiful.